What do you guys think? This is a Rubin Pod, 1,152 GPUs in 16 racks. Each one of the racks, as you know, has 72 Vera Rubin, or 72 Rubins. Each one of the Rubins is 2 actual GPU dies connected together. I'm going to show it to you. But there are several things that, well, I'll tell you later. I can't tell you everything right away. Well, we designed 6 different chips. First of all, we have a rule inside our company, and it's a good rule. No new generation should have more than 1 or 2 chips change. But the problem is this. As you could see, we were describing the total number of transistors in each one of the chips that were being described, and we know that Moore's law has largely slowed. And so the number of transistors we can get year after year after year can't possibly keep up with the 10 times larger models. It can't possibly keep up with 5 times per year more tokens generated. It can't possibly keep up with the fact that cost decline of the tokens are going to be so aggressive. It is impossible to keep up with those kind of rates if for the industry to continue to advance unless we deployed aggressive, extreme co-design, basically innovating across all of the chips, across the entire stack, all at the same time, which is the reason why we decided that this generation, we had no choice but to design every chip over again. Now, every single chip that we were describing just now can be a press conference in all in itself. And there's an entire company who's probably dedicated to doing that back in the old days. Each one of them are completely revolutionary and the best of its kind. The Vera CPU, I'm so proud of it. In a power-constrained world, Grace CPU is 2 times the performance. In a power-constrained world, it's twice the performance per watt of the world's most advanced CPUs. Its data rate is insane. It was designed to process supercomputers. And Vera was an incredible GPU. Grace was an incredible GPU. Now Vera increases the single-threaded performance, increases the capacity of the memory, increases everything just dramatically. It's a giant chip. This is the Vera CPU. This is one CPU. And this is connected to the Rubin GPU. Look at that thing. It's a giant chip. Now, the thing that's really special, and I'll go through these. It's going to take 3 hands, I think, 4 hands to do this. Okay, so this is the Vera CPU. It's got 88 CPU cores, and the CPU cores are designed to be multi-threaded. But the multi-threaded nature of Vera was designed so that each one of the 176 threads could get its full performance. So it's essentially as if there's 176 cores, but only 88 physical cores. So these cores were designed in using a technology called spatial multi-threading. But the I/O performance is incredible. This is the Rubin GPU. It's 5x Blackwell in floating performance. But the important thing is go to the bottom line. The bottom line, it's only 1.6 times the number of transistors of Blackwell. That kind of tells you something about the levels of semiconductor physics today. If we don't do co-design, if we don't do extreme co-design at the level of basically every single chip across the entire system, how is it possible we deliver performance levels that is, at best 1.6 times each year? Because that's the total number of transistors you have. And even if you were to have a little bit more performance per transistor, say 25%, it's impossible to get 100% yield out of the number of transistors you get. And so 1.6x kind of puts a ceiling on how far performance can go each year unless you do something extreme, and we call it extreme co-design. Well, one of the things that we did, and it was a great invention, is called MVFP4 Tensor Core. The transformer engine inside our chip is not just a 4-bit floating point number somehow that we put into the data path. It is an entire processor, a processing unit that understands how to dynamically, adaptively adjust its precision and structure to deal with different levels of the transformer so that you can achieve higher throughput wherever it's possible to lose precision, and to go back to the highest possible precision wherever you need to. That ability to dynamically do that, you can't do this in software because obviously it's just running too fast. And so you have to be able to do it adaptively inside the processor. That's what an MVFP4 is. When somebody says FP4 or FP8, it almost means nothing to us. And the reason for that is because it's the tensor core structure and all of the algorithms that makes it work. MVFP4, we've published papers on this already. The precision, the level of throughput and precision it's able to retain is completely incredible. This is groundbreaking work. I would not be surprised if the industry would like us to make this format and this structure an industry standard in the future. This is completely revolutionary. This is how we were able to deliver such a gigantic step up in performance, even though we only have 1.6 times the number of transistors. Okay, so this is, and now once you have a great processing node, and this is the processor node, and inside, so this is for example, here, let me do this. This is, wow, it's super heavy. You have to be a CEO in really good shape to do this job. Okay, all right. So this thing is, I'm gonna guess, this is probably, I don't know, a couple of 100 pounds. I thought that was funny too. Come on, it could have been. Everybody's going, no, I don't think so. All right, so look at this. This is the last one. We revolutionized the entire MGX chassis. This node, 43 cables, 0 cables, 6 tubes, just 2 of them here. It takes 2 hours to assemble this. If you're lucky, it takes 2 hours. And of course, you're probably going to assemble it wrong. You're going to have to retest it, test it, reassemble it. So the assembly process is incredibly complicated. And it was understandable as one of our first supercomputers that's deconstructed in this way. This, from 2 hours to 5 minutes. %, liquid cooled, 100% liquid cooled. Yeah, really, really a breakthrough. Okay, so this is the new compute chassis, and what connects all of these to the top-of-rack switches, the east-west traffic, is called the Spectrum-X NIC. This is the world's best NIC, unquestionably NVIDIA's Mellanox, the acquisition Mellanox that joined us a long time ago now. Their networking technology for high-performance computing is the world's best, bar none. The algorithms, the chip design, all of the interconnects, all the software stacks that run on top of it, their RDMA, absolutely, bar none, the world's best. And now it has the ability to do programmable RDMA and data path accelerator so that our partners like AI labs could create their own algorithms for how they want to move data around the system. But this is completely world-class, ConnectX. ConnectX-9 and the Vera CPU were co-designed. And we never revealed it, never released it until CX9 came along because we co-designed it for a new type of processor. You know, ConnectX-9, or CX8 and Spectrum-X revolutionized how Ethernet was done for artificial intelligence. Ethernet traffic for AI is much, much more intense, requires much lower latency. The instantaneous surge of traffic is unlike anything Ethernet sees. And so we created Spectrum-X, which is AI Ethernet. 2 years ago, we announced Spectrum-X. NVIDIA today is the largest networking company the world has ever seen. So it's been so successful and used in so many different installations. It is just sweeping the AI landscape. The performance is incredible, especially when you have a 200 megawatt data center, or if you have a gigawatt data center. These are billions of dollars. Let's say a gigawatt data center is $50 billion. If the networking performance allows you to deliver an extra 10%, in the case of Spectrum-X, delivering 25% higher throughput is not uncommon. If we were to just deliver 10%, that's worth $5 billion. The networking is completely free, which is the reason why, well, everybody uses Spectrum-X. It's just an incredible thing. And now we're going to invent a new type of data processing. And so Spectrum-X is for east-west traffic. We now have a new processor called BlueField 4. BlueField 4 allows us to take a very large data center, isolate different parts of it so that different users could use different parts of it, make sure that everything could be virtualized if they decide to be virtualized. So you offload a lot of the virtualization software, the security software, the networking software for your north-south traffic. And so BlueField 4 comes standard with every single one of these compute nodes. BlueField 4 has a second application I'm going to talk about in just a second. This is a revolutionary processor, and I'm so excited about it. This is the NVLink 6 switch, and it's right here. This switch chip. There are 4 of them inside the NVLink switch here. Each one of these switch chips has the fastest SerDes in history. The world is barely getting to 200 gigabits. This is 400 gigabits per second switch. The reason why this is so important is so that we could have every single GPU talk to every other GPU at exactly the same time. This switch on the backplane of one of these racks enables us to move the equivalent of twice the amount of the global internet data, all of the world's internet data at twice the speed. You take the cross-sectional bandwidth of the entire planet's internet, it's about 100 terabytes per second. This is 240 terabytes per second. So it kind of puts it in perspective. This is so that every single GPU can work with every single other GPU at exactly the same time. Okay? Then on top of that, okay, so this is one rack. This is one rack. Each one of the racks, as you can see, the number of transistors in this one rack is 1.7 times. Yeah, could you do this for me? So it's usually about 2 tons, but today it's 2.5 tons because when they shipped it, they forgot to drain the water out of it. So we shipped a lot of water from California. Can you hear it squealing? You know, when you're rotating 2.5 tons, you're going to squeal a little. Oh, you could do it. Wow. Okay, we won't make you do that twice. All right, so behind this are the NVLink spines. Basically 2 miles of copper cables. Copper is the best conductor we know. And these are all shielded copper cables, structured copper cables, the most the world's ever used in computing systems ever. And our SerDes drive the copper cables from the top of the rack all the way to the bottom of the rack at 400 gigabits per second. It's incredible. And so this has 2 miles of total copper cables, 5,000 copper cables, and this makes the NVLink spine possible. This is the revolution that really started the NGX system. Now, we decided that we would create an industry standard system so that the entire ecosystem, all of our supply chain, could standardize on these components. There are some 80,000 different components that make up these NGX systems, and it's a total waste if we were to change it every single year. Every single major computer company, from Foxconn to Quanta to Wistron, the list goes on and on and on, to HP and Dell and Lenovo, everybody knows how to build these systems. And so the fact that we could squeeze Vera Rubin into this, even though the performance is so much higher, and very importantly, the power is twice as high. The power of Vera Rubin is twice as high as Grace Blackwell. And yet, and this is the miracle, the air that goes into it, the air flow is about the same. And very importantly, the water that goes into it is the same temperature, 45 degrees C. With 45 degrees C, no water chillers are necessary for data centers. We're basically cooling this supercomputer with hot water. is so incredibly efficient. And so this is the new rack. 1.7 times more transistors, but 5 times more peak inference performance, 3.5 times more peak training performance. Okay? They're connected on top using Spectrum-X. Oh, thank you. This is the world's first manufacturing chip using TSMC's new process that we co-innovated called COUP. It's a integrated silicon photonics process technology. And this allows us to take silicon photonics directly right to the chip. And this is 512 ports at 200 gigabits per second. And this is the new Ethernet AI switch, the Spectrum-X Ethernet switch. And look at this giant chip. But what's really amazing is it's got silicon photonics directly connected to it. And lasers come in. Lasers come in through here. Lasers come in through here. The optics are here, and they connect out to the rest of the data center. This I'll show you in a second, but this is on top of the rack. And this is the new Spectrum-X silicon photonics switch. Okay? And we have something new I want to tell you about. So just as I mentioned, a couple of years ago, we introduced Spectrum-X so that we could reinvent the way that networking is done. Ethernet is really easy to manage, and everybody has an Ethernet stack, and every data center in the world knows how to deal with Ethernet. And the only thing that we were using at the time was called InfiniBand, which is used for supercomputers. InfiniBand is very low latency, but of course the software stack, the entire manageability of InfiniBand is very alien to the people who use Ethernet. So we decided to enter the Ethernet switch market for the very first time. Spectrum-X, that just took off, and it made us the largest networking company in the world, as I mentioned. This next generation Spectrum-X is going to carry on that tradition. But just as I said earlier, AI has reinvented the whole computing stack. Every layer of the computing stack. It stands to reason that when AI starts to get deployed in the world's enterprises, it's going to also reinvent the way storage is done. Well, AI doesn't use SQL. AI uses semantics information. And when AI is being used, it creates this temporary knowledge, temporary memory called KV cache. Key value combinations, but it's a KV cache, basically the cache of the AI, the working memory of the AI. And the working memory of the AI is stored in the HBM memory. Every single token, for every single token, the GPU reads in the model, the entire model. It reads in the entire working memory, and it produces one token. And it stores that one token back into the KV cache. And then the next time it does that, it reads in the entire memory, reads it, and it streams it through our GPU, and then generates another token. Well, it does this repeatedly, token after token after token, and obviously, if you have a long conversation with that AI, over time, that memory, that context memory, is going to grow tremendously. Not to mention the models are growing, the number of turns that we're using the AIs are increasing. We would like to have this AI stay with us our entire life and remember every single conversation we've ever had with it, right? Every single lick of research that I've asked it for. Of course, with the number of people that will be sharing the supercomputer is going to continue to grow. And so this context memory, which started out fitting inside an HBM, is no longer large enough. Last year, we created Grace Blackwell's very fast memory, we call fast context memory. That's the reason why we connected Grace directly to Hopper. That's why we connected Grace directly to Blackwell, so that we can expand the context memory. But even that is not enough. And so the next solution, of course, is to go off onto the network, the north-south network, off to the storage of the company. But if you have a whole lot of AIs running at the same time, that network is no longer going to be fast enough. So the answer is very clearly to do it different. And so we created BlueField 4 so that we could essentially have a very fast KV cache context memory store right in the rack. And so I'll show you in just one second, but there's a whole new category of storage systems. And the industry is so excited because this is a pain point for just about everybody who does a lot of token generation today. The AI labs, the cloud service providers, they're really suffering from the amount of network traffic that's being caused by KV cache moving around. And so the idea that we would create a new platform, a new processor, to run the entire Dynamo KV cache context memory management system and to put it very close to the rest of the rack is completely revolutionary. So this is it. It sits right here. So this is all the compute nodes. Each one of these is NVLink 72. So this is Vera Rubin, NVLink 72, 144 Rubin GPUs. This is the context memory that's stored here. Behind each one of these are 4 BlueFields. Behind each BlueField is 150 terabytes of memory, context memory. And for each GPU, once you allocate it across, each GPU will get an additional 16 terabytes. Now, inside this node, each GPU essentially has 1 terabyte. And now, with this backing store here, directly on the same east-west traffic, at exactly the same data rate, 200 gigabits per second, across literally the entire fabric of this compute node, you're going to get an additional 16 terabytes of memory, okay? And this is the management plane. These are the Spectrum X switches that connects all of them together. And over here, these switches at the end connects them to the rest of the data center, okay? And so this is the Vera Rubin. Now, there's several things that's really incredible about it. So the first thing that I mentioned is that this entire system is twice the energy efficiency, essentially twice the temperature performance, in the sense that even though the power is twice as high, the amount of energy used is twice as high, the amount of computation is many times higher than that, but the liquid that goes into it is still 45 degrees C. That enables us to save about 6% of the world's data center power. So that's a very big deal. The second very big deal is that this entire system is now confidential computing safe, meaning everything is encoded in transit, at rest, and during compute. And every single bus is now encrypted. Every PCI Express, every NVLink, every NVLink between CPU and GPU, between GPU to GPU, everything is now encrypted. And so it's confidential computing safe. This allows companies to feel safe that their models are being deployed by somebody else, but it will never be seen by anybody else, okay? And so this particular system is not only incredibly energy efficient, and there's one other thing that's incredible. Because of the nature of the workload of AI, it spikes instantaneously with this computation layer called all-reduce. The amount of current, the amount of energy that is used simultaneously is really off the charts. Oftentimes, it'll spike up 25%. We now have power smoothing across the entire system so that you don't have to over-provision by 25 times, or if you over-provision by 25 times, you don't have to leave 25%, not 25 times, 25% of the energy squandered or unused. And so now you could fill up the entire power budget, and you don't have to provision beyond that. And then the last thing, of course, is performance. So let's take a look at the performance of this. These are only charts that people who build AI supercomputers would love. It took every single one of these chips, complete redesign of every single one of the systems, and rewriting the entire stack for us to make this possible. Basically, this is training the AI model, this first column. The faster you train AI models, the faster you can get the next frontier out to the world. This is your time to market. This is technology leadership. This is your pricing power. And so in the case of the green, this is essentially a 10 trillion parameter model, we scaled it up from DeepSeek, that's why we call it DeepSeek++, a training a 10 trillion parameter model on 100 trillion tokens, okay? And this is our simulation projection of what it would take for us to build the next frontier model. The next frontier model, Elon's already mentioned that the next version of Grok 5, I think is 7 trillion parameters, so this is 10. And in the green is Blackwell. And here, in the case of Rubin, notice the throughput is so much higher, and therefore it only takes 1/4 as many of these systems in order to train the model in the time that we gave it here, which is 1 month, okay? And so time is the same for everybody. Now, how fast you can train that model and how large of a model you can train is how you're gonna get to the frontier first. The second part is your factory throughput. Blackwell is green again, and factory throughput is important because your factory is, in the case of a gigawatt, is $50 billion. A $50 billion data center can only consume 1 gigawatt of power. And so if your performance, your throughput per watt is very good versus quite poor, that directly translates to your revenues. Your revenues of your data center is directly related to the second column. And in the case of Blackwell, it was about 10 times over Hopper. In the case of Rubin, it's going to be about 10 times higher again, okay? And in the case of now the cost of the tokens, how cost effectively it is to generate the token, this is Rubin, about 1/10. Just as in the case of, yep. So this is how we're gonna get everybody to the next frontier, to push AI to the next level, and of course, to build these data centers energy efficiently and cost efficiently. So this is it. This is NVIDIA today. You know, we mentioned that we build chips, but as you know, NVIDIA builds entire systems now, and AI is a full stack. We're reinventing AI across everything from chips to infrastructure to models to applications. And our job is to create the entire stack so that all of you could create incredible applications for the rest of the world. Thank you all for coming. Have a great CES. Now, before I let you guys go, there were a whole bunch of slides we had to leave on the cutting floor, and so we have some outtakes here. I think it'll be fun for you. Have a great CES, guys.
And cut.
NVIDIA Live at CES Take 4 Marker.
Boom mic. Action.
Sorry, guys.
Platform shift, huh? That should do it.
And let's roll camera.
Ah, shade of green. A bright, happy green.
World's most powerful AI supercomputer you can plug into the wall, next to my toaster.
Hey guys, I'm stuck again. I'm so sorry.
This slide is never gonna work. Let's just cut it.
Hello? Can you hear me? So like I was saying, the router, because not every problem needs the biggest, smartest model, just the right one.
No, don't lose any of them.
This new 6-chip Rubin platform makes one amazing AI supercomputer.
There you go, little guy. Oh, no, not the scaling laws.
There is a squirrel on the car. Be ready to make the squirrel go away. Ask the squirrel gently to move away.
Did you know the best models today are all mixture of experts?